through the first week. And then
There was. I think this is like a feature of night classes where it starts out packed, but I think people start relying on the recordings as we're going. If you're curious how much are still in the class, only a couple people have dropped. We're at size 25. That includes me. So it actually hasn't changed too much. It's kind of strange.
you could close them if you're passing.
No, I couldn't. Yeah, at that point, that's the Federal Education Privacy Act law.
I could have to those up for you. They were asking me like, what were the symptoms? And I was like, I can't answer that. Takes the HIPAA or whatever. and all that.
Yeah, same concept, pretty much. Well, it looks like we can get started. Welcome back, everyone. So for today's class, we're going to be going through section 11.4. We're on example 2, but we're actually kind of midway through those notes. Then we're going to be doing something a little bit more tough. This is kind of the first big tough spot of the course, or excuse me, of the chapter, in chapter 11, alternating series and absolute convergence. The alternating series part is actually the good part. This is a nice test. It goes out really fast. It's not technical. But absolute convergence is technical. It becomes kind of nasty. So we're going to take our time with 11.5. We'll probably finish it sometime on Thursday is what it looks like on this one. So at the moment, this is what we have on the table. For the summary of tests for sequences, or excuse me, for series, we have test for divergence, geometric p-series, and we're going to be picking up this one in the next section. Currently, we also have comparison test, limit comparison test. Notice the alternating series is above. It's not the order. These tests are not in the order in which we covered them. They're in the order of which, if I give you just a random series, this is a good thought process of what to look through to find the best test. An alternating series, it's right up there with p-series. It's a very fast test, and if you can see that your test is, or your series is alternating, it's the best test to use. Sorry, I'm not sure where I'm clicking on there. But before we get to that one, we need to complete limit comparison test as our next one. So this is where we left off last time, right on this test. Any questions or comments first, folks, before we get started? Okay, so here's how it goes. We talked about a little bit what the logic is on this test. So let's do it again. When we take the limit of a ratio like this, and we get a finite number C, it does tell us something about the growth rates of A versus the growth rate of B. Sort of like the logic of L'Hopital's test in a certain sense. If we get a finite number C, it means that the sequence in the numerator, it didn't grow too fast. If it were to grow to infinity faster than the denominator sequence, we should have gotten infinity here. Likewise, if C is not 0, if it really is positive, that means sequence Bn couldn't grow too fast relative to An either. If Bn grows exceedingly fast, much faster than An, this whole thing would have been 0. But we've eliminated that condition at the same time. Essentially now what we're saying in the limit comparison test is the rate at which these change as n goes higher and higher is comparable if we get a constant. And if they're comparable, that means it's an honest comparison test itself. This one is a weird one. It uses the direct comparison test, the one right above, to prove this one. And the conclusion's a little bit different as well. The conclusion is similar in the sense that the fates of your series are essentially tied together. If one of them diverges, so does the other one. One of them converges, so does the other one as well. When you run this test, you're given that one, An. It's provided. So the conclusion that we give is on this right here. But we have to test it through another series. To know if this one converges, you have to know that Bn converges. Or to know that An diverges, you have to know Bn diverges because they have both the same exact conclusion. I should have boxed that one out as well. So what that means is when you use a limit comparison test, just like with the ordinary comparison test, we must also test this for convergence, divergence. And the thing that's hard about both comparison tests is you have to come up with that one as well. We've provided that series an, we come up with this one in a reasonable way, and then we test with whatever we come up with. But there is some guidance on how to come up with this series Bn. Here's how it could go. First, look at this one over here. You would almost never want to use an ordinary comparison test on this one because there's too many sign changes, positive with negative and positive, makes a comparison test really difficult if doable at all. What I mean by that is take a look in just to the very first problem. This absolutely diverges. But if I put plus right here, it still diverges, yet this estimate goes the wrong direction. The comparison test can't even be used with the plus right here. We would want to use the limit comparison test instead. So now when you see something with a lot of extra terms and different sign changes, this is a really strong indication that limit comparison test is probably the best and only way to go on it. So we'll begin by saying, compare to summation Bn, and let me actually take another step here. Let's call this one summation An, just so we can have some names. We need to name this stuff because if we're going to use this theorem above, we need to know what is what, or else we're going to be really struggling trying to compare constantly where things fit together. So give it a name Bn to take the same exact role as what we indicate above here. We'll set this one as a summation, starting at the same index 1, going to infinity. And now, here's how we form the Bn series. Imagine you were just taking the limit of 2n plus 1 divided by the 3n squared minus n plus 1. That limit would be 0. That's because the thing that matters the most in the numerator is 2n, lower degree than the one that matters the most in the denominator, 3n squared. Use that same logic and build out the series for Bn. Take the thing that matters the most in the numerator. That's just the n. The plus 1 is inconsequential when n becomes large, and it is getting large, it's going off to infinity. When n is going off to infinity, minus n plus 1 means very little, but that n squared means everything. I'm going to ditch the constants and just go n over n squared. If you did go 2n over 3n squared, it works just as well. It's just a little bit more work that's unnecessary. So I focus on, I said the constants. Yeah, I skip the constants, focus on the variable part, n power 1 over n power 2. So those are the most influential terms. And this becomes a summation from 1 to infinity of 1 over n. Even though the instructions here say we must test it, there is one out. If you know what series this is, you can just say what it is and state the conclusion for that named series. Anyone recall what this one is right here? Good call. This one's a harmonic known to diverge. But you know, some people might have done this. Some people might have said, that's a p series with p exactly 1. P less or equals to 1 qualifies, so it diverges. If you decide to go that route, totally fine as well. It might be even less writing. It's kind of funny in a way. But it's good to know about the harmonic series. It's a great counterexample, and it shows up all the time, like in this problem. So let's call it that. This is the divergent harmonic series. So we're done with that part. We know Bn diverges, and because it diverges, this conclusion's off the table. We're going for a conclusion of both of them diverging, as in An must diverge now. The only way we're going to get to that logic is we now do this limit above. So take the nth term for An, the nth term for Bn, form the limit, and we want a non-zero constant, also not infinity. So now we're in the limit comparison test. It's really just at this step, it becomes a limit comparison test. You can, at this, still be doing that step in the ordinary comparison test. But now, with limit as n goes to infinity, we're choosing a direction. Take An divided by Bn, becomes limit as n goes to infinity of, just write in what the An term is, 2n plus 1 divided by 3n squared minus n plus 1. We're dividing by bn, but here's a great time to save a lot of writing and space. We divide by bn, we just multiply by the reciprocal of that term. So I'd be multiplying by n over 1. And now it's a limit as n goes to infinity. We've probably done about 30 of these kinds of limits already in this course, and we'll do a lot more. Multiply n through in the numerator, it's 2n squared plus n. Denominator is unaffected, 3n squared minus n plus 1. And the common thing we would always say is that is a rational function. The value of the limit as we go to infinity is a horizontal asymptote. And this does have one. There's a tie in degree, numerator and denominator. So we get an output of 2/3 exactly. That's a fast way to do a limit, which is a good idea since we do so many of these. Next, we analyze the constant c. It's positive. That's the condition on both converge or both diverge. So the fact that it's bigger than 0 means the terms of this more complicated series grow at a rate that's comparable to the terms of the harmonic series. They're highly comparable, it turns out. So if this one diverges, so did this one down here. So that's our conclusion. The greater than 0 right here immediately tells us, something, hang on. I thought I was hitting enter and I hit something else. What is that? This happened in the other class. Let me see if I can fix that. Hopefully we don't have that going on whole class, but that was exciting. Okay, aside from the distraction, we got a constant 2/3 greater than 0. Tells us that this one matches that conclusion. So if you've got divergent here, you've got a constant bigger than 0, you can now say summation an must also diverge. So we did it, folks. This is a nice little symbol to use because you don't necessarily want to write that each and every time you have to call it or think about it and say a formula like this one above. You just want to give it a name and just start working with it directly. And this is the logic of the limit comparative test. It's really fast because instead of making estimates, that does take some ingenuity, you just do a limit, the thing we're really, really good at, get a value out, and you'll have a conclusion. Only requirements are this value right here, the red dot, cannot be infinity, and it cannot be 0. If that's the case, the test ran as intended. We'll try this a couple more times just to get the feel for it on a couple more examples. So let me take a quick screenshot here to here, just for the main points, and we'll practice it some more. But any questions at all, folks, on our first run?
C doesn't satisfy the conditions, we just have to move on to a different test.
You do, yeah. We would say test fails, there's no conclusion to be drawn, we have to try something else. Yeah, and that can happen with some problems. But usually, you know, the way it does happen is if you had this an right here, and you went to define bn, maybe we made some weird mistake and we went 1 over n squared instead of n over n squared. We made that mistake. This one would have converged. Over here, it would have been an n squared. That would have been an n cubed, and we would have gotten an infinity instead. So usually you're either getting a 0 or an infinity, only because we just made a mistake right at that step there. So the test might still work. We might want to just look into how we formed the bn series. Other questions so far? Okay, let's try this out again. Here is part B. Part B looks terrible because K is in there instead of N. That just feels extremely jarring, but it's a good way to write this. We have to just remind our brain that a different symbol doesn't change the algebra or the calculus, just a new way to view this one. So using the limit comparison test, let's see, first thing we should do is make sure we have enough space for this one. I don't think we do. That should do it. First thing we should do for using any comparison test is write down some variables because there's just too much going on for our mind to track unless you're already really good at this kind of work. I'm not. I have to give my mind an upper hand by showing where things fit in. So I really need to name that, or else everything here gets pretty foggy. So once we have that, we'll say using limit, let me spell that right, limit comparison compared to summation bk, and I notice I already made a mistake. I want to call this an because I'm looking at an an down here. But if you change from n to k, it is jarring, right? Here's the first problem. All of our subscripts have to change. That's ak, not an. So now over here at bk, this becomes a summation as k goes from 1 to infinity. And we're going to use that same strategy. At the numerator, as k gets very, very large, plus k starts to have almost no impact on the numerator. It's all about the k squared. So throw that in on top. Denominator is a little bit more tricky though. It's not k7 that we're most interested in. It's the square root of k power 7. So we could write that in as k power 7. But because there's a square root in this problem, say 7/2, that's a great way to indicate it. Then if you went that route, this is starting to look like a p series now. Let's call this k goes from 1 to infinity, k power 4/2, k power 7/2. If we're going to analyze this as a p series, base k should be just in the denominator. So we'll divide it in this way. K runs from 1 to infinity, 1 over k to the power 3/2. It's now a p series altogether because we have a base raised to a power. Let's take a look into the p series analysis. If you're imagining this is a real exam problem, this is the actual page you might actually turn to on exam 3. So it's a good one to have printed out as just available. You want to orient yourself on this one since it's part of the handout. Next, on p series, you have to match that structure. That's what we have over here. Convergent if p is bigger than 1. That's 3/2 at bigger than 1. So let's say p series. That indicates we're using the p series test. Steps of the test are just to say what the power is. 3/2. Really smart idea to write the condition on convergence. It's greater than 1. So this means summation bk converges. So we have a convergence series. That means we might expect this one to converge as well if this is really as similar as we think it is to that. So that's where our estimate here on bk is going to matter when we go to do the limit. If you're copying the strategy I'm taking of just taking the highest degree term in the numerator, most influential term in the denominator, including the square root, you'll be on the right track. It's now all about the limit. Any questions first, folks, before we give it a try? Okay, so here's this key step. Limit as, oh darn it, not n, but k goes to infinity. It's amazing how much your brain just gets used to by muscle memory, writing down things a certain way. So go ak, divide by bk, and then this would be a limit as k goes to infinity. Here's the ak part first. 2k squared plus k divided by the root of 4k power 7 plus 3 divided by bk, which means multiply by this as a reciprocal, k power 3/2 divide by 1. In view of k power 3/2, we can correct these exponents. This k is to power 1, so raise it to 3/2. Or excuse me, we'll raise it to 2/2. That probably would help us a little bit better. More compatible with this one. This one's power 2, so we can change it to 4/2. Same exponent, and now it's compatible with that. So multiplying through in the numerator gives us limit k goes to infinity, let's hide the comparison test for just a moment. Limit as k goes to infinity of combining the powers in the numerator is 2 k power of 7 halves plus k power 5 halves. So that's our entire numerator. Kind of nasty in a way. This is not a rational function any longer, unfortunately. Denominator is the root. Same thing, 4k7 plus 3. So we need to do the limit of this one. But the thing that we've been doing on all of our limits has been to say, because this is a rational function, it has an asymptote. But that's not a rational function at all. We need to work a little bit more cleverly. However, there's even a shortcut on this one. The shortcut only works because the limit is going to positive infinity. The direction was negative infinity. The asymptote you think you get is actually opposite in sign. It's kind of interesting in a way. But I want to show this in a couple ways. First, here's the shortcut. It's a pretty big one. But we would use the same kind of strategy. What's the degree in the numerator? Well, I can't say degree any longer. It's not a polynomial. But the highest power is 7 halves. What's the highest power in the denominator? 7 halves as well, essentially, when you bring in the root and ignore a constant 3. That means there's essentially a tie in powers above and below. You would then grab the coefficients, 2 and 4, go 2 over root 4. So that means this is just 2 halves equals 1, and your job is done. That's bigger than 0, because this one converged. This one must also converge as well. But that one was really, I think the emphasis here is appropriate, a pretty major shortcut. This time, let's do it the full-on way that the author would have done if this is a real textbook example, just to show the process. But if you like this shortcut, the reason I put it down on paper is you're allowed to take it if it makes sense to you. Well, let's keep on running through this limit. It's a limit as k goes off to infinity. And here's another way to do this. We're going to analyze this limit by just analyzing the denominator. In the denominator, k power 7 is the most influential term, however it's square rooted. So we do this. Take root 1 over square root k power 7 and multiply it against 4k power 7 plus 3. That's how we handle the denominator, just doing that multiplication. And the numerator, we're going to handle it slightly differently. There's not too much I can do with color coding. Let's just keep going with this. And the numerator, take 2k power 7 halves. And let me just fix this. I need a little bit more space there. 2k power 7 halves. We're dividing it by this. I mean, we have to maintain the equality right here. We can't just divide on one spot and do something different up here. But the way we want to write this in is k power 7 halves. That's just another way to write this in. It's more convenient over here. The radical symbol is more convenient down here because algebraically, we can distribute not that, this. Sorry, this is the better way to write it. Root 1 over k power 7, they're equivalent answers, but this is more helpful. This entire root can distribute inside. Well, the radicand, 1 over k power 7. Over here, go plus k power 5 halves, k power 7 halves. And here's our next step. It's now the limit. As k goes to infinity, let's handle the numerator. It's easier to look at. Cancellation over here for just a 2, plus a reduction here, but you want to consolidate to the denominator. 1 over k power, well, that would be 2 halves, just k itself, really. Over here, here's the distribution step. This multiplies to here and to here. So now it's over a root. 4k power 7, k power 7, plus 3 over k power 7, which means a little bit more of a simplification just to show this better. Last step, this is equal to the limit. as k goes to infinity, 2 plus 1 over k over the root of 4 upon simplifying right here, plus 3 over k power 7. That's a lot of work, right? But we're finally where we want to be. We take the limit as k goes to infinity. That would converge to 0 because we're constant over something growing without bound. Likewise, numerator is bounded by 3. It's constantly 3. Yet the denominator grows without bound. So this converges to 0 as well. And we get the 2 and root 4 as the survivors on this. So this is 2 over root 4. We're finally where we would have been on the shortcut. It's nice to see how the shortcut works. And it's nice to see you don't have to do that if you don't want to. It's going to be your judgment call and homework questions for this kind of problem. We'll get 2 over 2, which is a 1. Now looking at the test finally, let's bring it back. 1 is greater than 0. It's a finite quantity. That means the test has succeeded. We're right here. Greater than 0. So now it's either they both converge or they both diverge. What was our conclusion? Convergence. So convergence here, getting a quantity greater than 0, tells us the original thing AK must converge now. There's no question about it. So let's come down here and say, this finally implies summation AK must also converge. Let's put an exclamation on it because it looks like we worked pretty hard on this, and I would feel, yeah, we really did. This was a tougher problem just because the limit is challenging. It's more challenging putting together the BK series as well. But once all the parts are in the right spot, this is the logic. We said we're using the limit comparison test. So convergence here is justified through that test specifically. We compared it to BK. This is showing the steps of limit comparison test. But you also have to test this series because it converged. And through the limit down here, we're now on the conclusion both of them have to converge. That's what allowed us to go over here on AK and give a convergence conclusion on that one as well. But it's an impressive amount of logic for one simple little problem. It's only because we're now stitching together multiple tests already on this section 11.4. Any questions at all, folks? Finalizing that answer there. Okay, and these weird purple directed light segments, that's just us analyzing portions of the limit comparison test, getting to those right conclusions. If you like arrows, that might be a decent strategy when you're working on these kind of problems. Let's try this out one more time, and then we'll switch gears into a review problem. Just like the original comparison test, sometimes these problems are really hard to even start. And this is one of those really weird problems, sine 1 over n. It's hard to know what fits this thing, but you know if you took the limit of this as n goes to infinity, you get sine 0, which is 0, and all that tells us is you can't use limit compare or the test for divergence on this one. We don't get a non-zero limit at all on sine 1 over n. So it looks like it really does fit the limit comparison test. There's no easy way out of this one. Let's say here, compare to summation bk equals summation. Oh, and I'm forgetting now, this is muscle memory, I guess. We're at bn, indexes are n now, which is equal summation as n goes from 1 to infinity. Something. This is the downside of both the original comparison test and the limit comparison test at the same time. There's no formula to tell you exactly what to pick right here. On the last two problems, we used more of a process. If it looks like a fraction or rational function, grab the dominating terms in the numerator denominator. But this is no fraction, no rational function. It's hard to know what to pick. Definitely open to suggestions. Any volunteers for something to try? Just an ordinary sine n. So if we go Sign in on that one. I like that thought. This one would be, let's see here, would that converge or would that diverge?
Cause we could probably like the same logic that we did with the comparison test, where you say it's bounded between. Well, it'll only approach a zero, but it never actually goes to zero for the whole integers.
This one right here?
No, the one we did originally, like. Cause you said sign was bounded between zero and bird. Oh yeah, you're right. There was a bird.
Oh, I see what you're meaning. Yeah, that one problem way above. Yeah, I think we could test this one for convergence, but I'm not sure what that nice test would be. I wouldn't see what it could be. Oh, wrong screenshot there. Doesn't fit this one because the limit as n goes to infinity just does, oh, hang on. The limit as n goes to infinity does not exist on sin n. It just oscillates. It does fit test for divergence. So this one is an immediate one that we can test on. So let's run this out. Limit n goes to infinity. Let's say bn, just as a way to indicate we're talking about this series right here. This becomes limit n goes to infinity of sin n. And this is a full-on does not exist. Terms oscillate between -1 and +1 endlessly. More to say there. You want to also say it's oscillating between these two values. Doesn't actually ever hit them, but it is between those two values, and it's not getting closer to any number necessarily. I feel like that's being conveyed here, especially if you see sin n. If you want to say every little thing about it, that's the next thing you would have to say. Let's actually put it down. Moreover, it does not approach any number. So what we're saying about that is the dots are just doing this. The amplitude isn't going down to a fixed height, for example, that would give us convergence on that height, just an endless oscillation. But now we have a conclusion of, sorry, say again? It definitely does, but we're only putting in integer values. So it's kind of those weird things where exactly, we'd have to have that irrational numbers to hit it. So it's getting pretty close, but never just hitting it directly. Kind of a weird process. So we have a limit that does not exist. This immediately implies summation bn diverges by test for divergence. That always feels kind of redundant, but that's us indicating the test we used. Now here's the downside, however. With whatever you come up for the bn series, we take the nth term and we have to form this limit. So the success of this as something to compare it to is going to fully depend on, can we do the limit? Limit as n goes to infinity, sine 1 over n, divide by sine n. That's one where I would probably have to really think about this one. How would you even do that limit? What is happening in the limit? As n goes to infinity, we have 0 in the numerator, does not exist in the denominator. That's a huge problem for us, because if this limit does not exist, we don't hit that conclusion and we don't hit that conclusion. We want a limit that really does exist. So we're kind of stuck on this step. This might be a good one to come back to. I have a feeling it might not exist, but that's no guarantee either. Sometimes these limits are truly very, very hard to calculate. In fact, the limit as n goes to infinity sine 1 over n, that's not an easy one either. We're using lots of tools to show that. So at this point, I'm open to suggestions. Any volunteers for something to try on this limit here? By 1 over n, how do you mean?
Oh, no,
Oh, I gotcha over here. Yeah, I think that might be a good way to try on this one up here. On this one, it seems like we're stuck. I'll just leave it like this unless someone has an idea to try on it. Stuck. So we will try another summation Bn. You know, if this ever happens to you on an exam setting though, if you're running out of time, just leave everything on paper like this because it's really good progress. It shows great understanding of limit comparison test. You're just simply stuck and you can't go to the next steps. If this was a 10-point problem, you probably got 7 out of 10 points to that step. But on a homework problem, we really have to find out another Bn. So we'll go with your suggestion. Let's try 1 over n. So let's say attempt 2. This is unfortunately kind of the par for the course on a comparison test. No guarantee we know exactly what we're comparing to and no formula to tell us. We just have to try something. It's trial and error, truly. So attempt 2, compare to, summation Bn is going to be harmonic series once again. Summation, n goes from 1 to infinity, 1 over n. Second time this came up on these notes, and let's analyze it a different way if it's come up a second time. You could just say converges by the harmonic series, or there's a fancy way to do this one. You can just say it's a p-series with this condition holding, less than or equals to 1, because the power right here is a 1. So p-series, p equals 1, which is indeed less than or equals to 1, which implies it diverges. So that's the condition on divergence for p-series. So now we're thinking that probably diverges, but we really are in the same situation. It's just going to depend on, can we do that limit? How approachable is it in the first place? It's nice that, well, it's nice to know that the limit of 1 over n does exist. It comes out as a 0. That might be able to help us. We'll see what actually happens on this one. Take the limit as n goes to infinity of an. Got to give this one a name. Let's call it summation an real quick. Divide by bn. It turns into the limit as n goes to infinity of sine one divided by n in the numerator. When we divide by bn, we could always multiply by the reciprocal like we've been doing before. But this time, let's do it directly. Let's just put in 1 over n into the denominator. This problem might look a little bit familiar to you. This one is not an easy limit either. It's hard like this one is hard, but there is an approach that I can see on this one. Let's take a look at what happens to the numerator. As n goes off to infinity, sine 1 over n converges to sine 0, and sine at 0 is 0 itself. And then in the denominator, as n goes to infinity, 1 over n converges to 0. That means this entire limit is indeterminate. And the indeterminate, say, is of type 0 from the numerator over 0 in the denominator. That's actually a good thing because now we have an extra tool, L'Hopital's rule. It's not too different from the logic of the original test right up here. In this test, we're comparing growth rates of what's happening in the numerator and denominator. Let's see if it's comparably growing. And in L'Hopital's rule, we're looking into sine 1 over n divided by 1 over n, but we take the derivatives of them. We're looking directly at the growth rate of sine 1 over n versus 1 over n in the denominator. So here's the L'Hopital's rule step. Take the limit as n goes to infinity. We take the derivative of sine 1 over n. That's a cosine 1 over n. It's also a chain rule. You have to multiply by the derivative of 1 over n. Notice I didn't compute it though. It seems like a kind of a cop-out. That's a weird thing. Usually you would compute that derivative right here in line. But in this problem, we don't have to. Because in L'Hopital's rule, the derivative of 1 over n is written that way. So there it is. And we get a direct cancellation from those two parts without even doing the derivative. We just indicated that it's there and it cancels. So now it's a limit as n goes to infinity of cosine 1 divided by n. But cosine is a continuous function in the variable n. And so we really are taking the limit of the inside. 1 over n goes to 0 as n goes to infinity. That means it's cosine 0. Here's where our trig is really important, right? Let's take another look at this test. The limit that we want to see come out has got to be positive. The moment it's 0, it has failed. So if we were looking at sine 0 and correctly put in the wrong value, we might have tricked ourselves into a big problem. But cosine 0 is 1, and so we are just fine on this one. If it's 1, then this will imply we had a conclusion of divergence originally. That means we have a conclusion of divergence on this one as well. Let's say here, summation an must also diverge by the limit comparison test. We never indicated what test we were using, so you can put it anywhere, at the top, the bottom, in the middle, completely up to you. As long as you say it, you're on the right track. So it's this condition of divergence, along with the limit coming out as a positive, non-zero, non-infinity quantity that gave us divergence down here finally. But it's a really bizarre one, right? This kind of question could never work as an exam problem because it takes way too much guesswork to even get started on it. But these kinds of things could be valid homework questions, however. If you ever feel like you're just not sure what to compare it to, don't hesitate to send the email. There's no secrets about these. Try it out first, and if you get stuck, I'm really happy to help. Well, that's the comparison test. It does feel it's convoluted because, let me undo that screenshot, you're dealing with two things simultaneously. So there's a lot of additional mental noise you have to navigate through to really use this effectively. Color coding and just simply naming your series like we're doing, summation an, summation bn, are really big helps with this kind of theorem. Well, what we'll be doing next is a gigantic review problem, example 3. Before we jump into this one, any questions at the moment, folks? Okay, we've got a lot on the table so far now with all of these tests, and we're seeing how the tests also interact. That's part of what makes this a pretty challenging concept in chapter 11. So now the best protection to really retain this knowledge is to constantly review this stuff as you go. Every time we pick up a new test, we'll do something along these kind of lines. So we have 6 tests that we can use. 6 series down below. Let me zoom in just a bit more. And all we're doing is a matching problem. Now, some of these can apply to more than one series. So it's a bit of an optimization problem because we're trying to match in this way. So even if we see something that might fit, we're looking for the test that fits the best. Maybe the easiest one to spot could be, where's our geometric series at? Anyone see which row and column a geo series could be? Top and middle? Good call. That one is absolutely geometric series. What makes it a geometric series on this one, good call, folks, is that right there. So here, we're not testing these series unless we want to. We're absolutely welcome to do so. That'd be a good review problem. Point of this problem is just to say, what's the test? Geo series test on this one. So the purpose to example 3 is when there's so many tests on the table, we have to see what tells us the difference between them. So that's what makes a geometric series. The idea here is n is an exponent. Maybe the next easiest one to see is the p series. But sometimes you have to do a good amount of algebra to really see it as a p series. The feature here, though, is that n is the base. And we want to get to something that looks like this, 1/2 n raised to some power. Anyone see which of the six is a P series? Turns out this one is very close to a P series.
Alright.
Yeah, the -8 kind of messes it up. Maybe we could re-index it, but the power 3 makes re-indexing kind of challenging on it as well. So what would be the one that's even more similar to P series? Anyone see the one that's kind of like this, but more directly in that form?
Top left.
It is top left, yeah. So this one up here in the corner, this is the P series. What makes it a P series is that's n power 1/3. That's n power 1. So you could do some algebra and get it to that structure right there. So this one, because of this, and because there's really a power 1 right there, actually, let's say it a better way. We're focusing on n being the base. I think that's a better concept because n is a base here to power 1/3, and it's a base there to power 1. We would use P series test. So that's 2 down. I'm not too sure what the next easiest one would be, but maybe let's reserve this for the worst one. Which one is the worst one amongst the 4 here? Because that's the one you'd want to use the integral test. It's the one where nothing else is going to even come close to fitting. Comparison test is off the table, in other words. Anyone see the worst series here that deserves an integral test? Yeah, top right, we could do an integral test on that one. Is that the best test on that one? Maybe so. But if we did top right on integral test, the next question would be, what test would we use on that one then? It turns out it's close, but with the n in the numerator, it's no longer geometric. Same with P series. With e to the power of n, it's no longer a P series either. And using a comparison test to fix that situation would probably involve a lot of creativity on that. I don't know how I would use a comparison test to get it to a P series. In my view, that one actually might be the worst one. Although integral tests should work just fine on this one. It's kind of hard to tell. I almost want to apply integral test on both of them because I know a good U substitution would work on this, but integration by parts would work on that one as well. It's a really tough one. How about, let's say it's a tie for now. We'll come back to that one. Let's see if we can do a better designation. So 4 might be one of those. Let me put down the numbers just for a better correspondence. Let's maybe move on to, how about that one? Test for divergence. Anyone you see that looks like it worked the best with test for divergence? Yeah, that one looks great because if you take the limit of this, the limit's 2/3. Let's look at the test. Test for divergence wants a limit that's not 0. And when that happens, you get divergence. So we can, by visual inspection, just see that's a divergent series immediately because the limit's 2/3. So this would be a really good one for test for divergence. In fact, this test is so fast. Let's run it. The limit as n goes to infinity, 2n, 3n minus 1 is 2/3. Here's that common shortcut for dealing with rational functions. So this is not 0. It means it diverges. So we ran the test on that one. That means there's just 3 more left over. We've got integral test that looks like it can work on both, a comparison and a limit comparison. Okay, any volunteers for which one to put, say, a comparison test on? This one right here? Yeah, this one looks like it converges. If it converges, we want to say n cubed minus 8 less than n cubed. That is true, right? And then when we take the reciprocal, 1 over n cubed minus 8 would be greater than 1 over n cubed. That actually looks problematic. This tells us comparison test isn't going to work on this one, even though it looks great. That's because if this is Bn, the series for Bn would converge. It's a P series with P at 3. But we have something that's bigger than a convergence series. We want something being smaller than. That's really unfortunate, right? That's the downside of the ordinary comparison test. If that was a plus, everything would work better. And yeah, I agree, if we're not getting the original comparison test to work, we'd use a limit comparison test instead. So let's upgrade it to a limit comparison. Call this one 6. Limit comparison test. Only because the estimates failed. I agree, it looks like the comparison test initially seems like the better test. And if it's a plus h like that, it really is. The comparison test works just fine. It's almost not fair that the comparison test is so finicky with those kind of estimates. But now we're down to 2. If we call this one the integral test, we would have to use the original comparison test on that thing. I bet you that one's actually easier. Let's check this out. I wouldn't have said so at the very start, but it looks like this one is good for the comparison test. Let's see if we can run through the logic on this one. We would say n squared plus 1 squared is certainly bigger than n squared squared, which is n power 4. Let me see if I can move something down. No, it looks like I'm kind of constrained on my space here. So if we take the reciprocal of both sides, we have 1 over n squared plus 1 squared less than n power 4 over 1. And if we multiply both sides by n, we're not changing this direction because n is always positive. Times n times n. Now, if this is summation an, we have an over here. It's less than 1 over n cubed, which would be bn over here. And that's a good enough numerical evidence for us so far that comparison test does work on this one. That's the right estimate. This would converge because this as a series is convergent. P series with P3 larger than 1. So this one was really hard to tell. It turns out this one is 5. Hard to know even where to put the number. This one is 5. Comparison test. Pretty strange, right? If I looked at that, I might have said integral test or limit comparison test, ordinary comparison test on this one, but actually thinking about how you run through the test totally changes our options on these. That means finally the integral test, the one that takes the most steps, the most time, the most thought overall, should be that one. I would say this is a convergence because we have an exponential function in the denominator with just a linear in the numerator. It should converge, but then we would have to show all details of that test to really come up with that conclusion. Well, that was our review and rundown, folks, of just seeing how the tests match up with the random series right in front of us. This is kind of like the experience of doing an exam. These things are mixed up. You'll get them mixed up. It's all about the process of finding what fits. I'm not going to give overly complicated series on the test, so if you can tell them apart just on this problem, it means your studying is really on the track for exam 3. Last question for the class then. Any one of these you want to try a second time? Or any one of these you want to do as a full test before we go to the next section?
Out of curiosity, you're going to limit comparison test on the top right one?
This one up here? Yeah, I believe a limit comparison would work just fine. Yeah, which means even though you can do comparison test, if I had to show the details on this one, I probably would personally just use limit comparison on it. It's rapid, and the estimates here are a little bit more finicky. You have to be a lot more careful on those. Any other questions so far? Okay, let's save this up and take a look at what we're getting into in the next section. We can already see from this document immediately what's coming up next. Next concept is alternating series test. This is a fantastic test. It's kind of like a P-series or geoseries or test for divergence. Not a lot of steps to show, except maybe what makes this test a little bit trickier is you have to know you have an alternating series in the very first place. But also notice what this alternating series test resolves for us. Let's look into some of these conditions here. If we're looking into the comparison test, that's a massive important conclusion, or excuse me, part of the hypothesis. Both of our sequences have only positive terms, and so same with the series. Same with the limit comparison test, positive terms. Same with the integral test. Let's see here. The function is positive. The sequence matches up with the positive. The sequence is positive as well then. This all seems really restrictive when you think about it. One thought you might have is, if everything has to be positive, how would you use the comparison test on, say, summation negative n cubed n squared plus n power 4 plus 5? I mean, you can't, right? There's a negative sign. But really you can. You just change it to a new series, summation n cubed n squared plus n power 4 plus 5. If the one on the right converges, then multiplying by a negative sign, which is multiplying the total sum by a negative sign, it would converge as well. Not as restrictive as you think. The actual big restriction is right here. Once I find the eraser tool. The big problem where it keeps on saying positive terms is whenever this comes up. Now this one has some terms positive, some terms as negative, and it alternates positive, negative, or negative, positive forever. Simply factoring out a negative sign is not going to work with this at all. This is where the alternating series test finally comes into play. It's all about that part right there, alternating. So let's give this a try then on the next section. We're in 11.5 now. First thing we have to carefully define again is what is an alternating series in the first place. We'll say that this series is alternating if we can write it in this form right here. So the alternating part is that negative 1 to a power. The Bn that you produce has to have positive terms for all n. It might not be the case until maybe n is 5, then all terms after 5 that qualifies. If that's the case, then this still matches that condition. So we take an, we re-express it in this way, factor out the positive part, the alternating part, and that's what makes this suddenly an alternating series. So in this position, negative 1 power of n, it could be exactly that, or any kind of algebraic variation that still allows alternation. So these are things that could come in as well, right up here. So that means on part A, all we're doing on this example is determining, are these alternating or not? This one is absolutely not alternating whatsoever. This one is just always negative. Actually, instead of just saying always negative, let's just write it out and show it. If we were to expand this, it's a series, that just means we're adding together infinitely many terms. Plug in 1, and it's negative 1 over 1. Plug in 2, and it's going to be a negative 1 over 2, negative 1 over 3, negative 1 over 4, and so on. This tells us it's not alternating. Simply because all the terms are negative on this one. If something was only positive terms, it's also not alternating. So the takeaway with part A is just because there's a negative sign does not mean you have an alternating series in this sense over here. Another trouble, however, is it doesn't have to be written with a negative 1 to a power. The fact that it alternates could be hidden from us. And so if we see a cosine function, it may or not be alternating. It just depends on what's inside the function. Say, for example, you had something that goes like this, just as a quick example. Let's write out a fast sequence that goes cosine. Let's make this be n pi. As n goes from 1 to infinity, terms of this one would look like this. Plug in 1, it's cosine pi, so it's a -1. Plug in 2, that's 2 pi, that's a +1. Plug in 3, at 3 pi, we're back to -1. And it just alternates in that exact pattern over and over and over again. So that's an alternating sequence, which tells us summation n from 1 to infinity, cosine n pi is an alternating, that looks like an M, let me fix that real quick here, alternating series. However, just because you see a cosine function doesn't mean the series is alternating. Part B is not, and it's kind of surprising in a way. It's cosine n over n squared plus 3. If we expand out these terms, this is what we get. Cosine 1 over 4. Plug in 2, it's cosine 2 over, this is the harder part, so that'll be 7. Cosine 3, that's going to be a 12 plus cosine 4, that's a 17, and so on. As it's written, I can't quite tell if this is alternating or not, but I would doubt it. To get a cosine function or a sine function to alternate, you usually need a little bit more stuff inside. That pi there, n times pi is what forced the alternation. And let me just fix that little thing there. There we go. Now looking into this a little bit more closely, take a look into cosine 1. That's positive. Cosine 2 is negative. It's alternating. Cosine 3 is negative, and that is enough to show a pattern break, that alone. Both these terms are negative. The negatives don't actually alternate on this. It looks like they double up, and they probably don't always double up either. It just depends on where on the unit circle is 3 radians, 2 radians, and 1 radian, and so on. The geometry is making this a really hard one to analyze. So here we'll just say negative and negative there. Therefore, series is not alternating. So sometimes the fact it alternates is not easy to see. If cosine or sine comes up, you want this kind of stuff to show up as well. So if I did a sine version, it would be n pi over 2, for example. Then last one is this thing right here. But this is a dead-on giveaway, isn't it? If it just exhibits -1 to a power, and that power involves n, not this one, where -1 is just hanging out, not being affected whatsoever, then this one directly alternates. E power of n in the denominator is always positive, so it's not going to mess up the alternating part at all on this one. This one is alternating. So that's how it goes. We now know how to determine if we have an alternating series. Unfortunately, page 1 of the notes didn't say how to analyze it. That's going to be the next page. But this is the important first step. How do you know you have an alternating series in the very first place? Much like if you're going to analyze these series, you have to know which one is a good P series, which one is a good integral test, and so on. It's all about being able to categorize them as you see them. So now finally, the actual alternating series test goes like this. Like I mentioned, it's a nice test actually. If you have an alternating series in this form, here's what makes it alternate. We pick up a new portion, Bn, which is going to satisfy this hypothesis. Bn has to be decreasing. The limit of Bn has to be 0. And if all that happens, you get convergence. Well, it turns out the one down below converges, and it in fact has a name. This is only the second name series, and it's going to be the last one. This one is called alternating harmonic series. And anytime the alternating harmonic series comes up, except for this time, we're going to show this one converges directly when we come back on Thursday. But anytime thereafter, it's like the original harmonic series. This shows up all the time, especially once we get into power series and Taylor series and Maclaurin series. You don't have to test it every single time it comes up. If you know the name of it, you can just state the conclusion. This is known to converge. Whereas the original harmonic series is the divergent example. Somehow, if you put something alternating inside what was a harmonic series, you get convergence. So we'll look into that when we come back a little bit more fresh on Thursday's class next. But any last questions, folks, about alternating series so far? Okay, so we'll come back here, finish these off, but then the hard work we'll do on Thursday is right here. Absolute convergence is a finicky topic. What makes this problem pretty difficult is you're essentially going to have everything on the table all the way through here for these new problems, determining absolute convergence versus conditional convergence versus divergence is actually a pretty big problem. So that's what we'll be spending most of our time on next Thursday. But have a great night, folks. We'll return to this next time.
It's gonna be very. Oh, wow. 1,800 calories.